Okay, so this work is about compositional pre-training for neural semantic parsing. Semantic parsing is basically going from natural language to logical forms, and it has applications in question answering, instruction following, and code generation. The unique challenges with semantic parsing are that the decoding needs to be constrained because we're dealing with logical forms. We have to make sure that we're generating valid logical forms. Also, another challenge is that the sequence-to-sequence architectures that are very pervasively used for this problem don't allow for easily injecting prior knowledge. So the data set that I've used for this project is called GeoQuery, which is a set of questions about facts about US geography paired with a Prolog query. So here you can see the question is, what is the capital of Alaska? And you see the corresponding Prolog query. So in terms of approach, I've used a sequence-to-sequence architecture with an attention copying mechanism. The encoder is bidirectional LSTM with 256 hidden units. The token embedding size is 64. And we're using an atom optimizer with learning rate of 0.001. And we did some hyperparameter search with all these parameters, and this was actually the best combination of hyperparameters. So the evaluation metric is called sequence accuracy, which is basically an exact string match for the predicted sequence relative to the true sequence. And I'm using a few augmentation strategies to allow for injecting prior knowledge into the model. So these include things like replacing the entity with its type and also concatenating the same sequence over and over again. In this example, we're actually only using 2. So we're concatenating the same sequence by itself just once. And the novel augmentation strategy we're using here is called co-occurrence. The intuition is pretty simple. So we're just saying if a token appears in very similar contexts, then we're going to link those kinds of tokens together and replace them in both the source and the target. So for example, if you have something like Ohio, what is the highest point in Ohio? And we've seen Ohio co-occurring with other states, we will just be going ahead and replacing it with those states and generating these augmented sequences. So in terms of results, we actually saw that pre-training the model with these augmented examples and then fine-tuning on the actual task is very beneficial. So we see the highest sequence accuracy within our set of experiments is when we have pre-training and augmentations. So in terms of error analysis, we the graph on the left is basically telling us what's the intersection over union of the unique tokens between the source and between the predicted and the actual logical forms. And here you can see that we are, for the most part, generating most of the necessary tokens, but they're not always generated. And it doesn't, just generating the tokens doesn't tell you if the nesting or the order is correct. So the graph on the right tells you that as the nesting of the logical form gets deeper, so this is basically how many opening parentheses we have as a proxy for the nesting or the complexity, it's harder and harder for the model to predict the true logical form. So in conclusion, we've shown that pre-training with augmentation is actually beneficial in terms of future work. We can expand this work to, in the pre-training phase, do unsupervised monolingual training, both the decoder and encoder, and that allows us to do this with larger data sets and across multiple tasks. And that is a promising area, and inspired by works like BERT, it should allow us to get to better semantic parsers.